Welcome to qnawire.
So once again, welcome to a new problem. This time you have a cow, like a cow. Okay, so it's leaving the barn. So this is the barn, and we'll say that the barn happens to be at x equals to 0, and then it's traveling that way, and you're trying to stop it. You're trying to stop it. You're trying to push it and stop it from leaving the barn. So you're applying a force against the cow that way. You're applying a force in the horizontal direction. The funny thing is that I don't know how strong the cow is, but if you're pushing it, the force is not going to be constant. It just depends on how strong the cow is. And so that force that you're applying on the cow, this one right here, we're going to call it f of x. It happens to be negative 20.0 Newton. It's a variable force that's dependent on the displacement, and that's why you're seeing on the force itself there's a parameter with an x on it. So it just means that the there's an x component in terms of displacement that's affecting the force itself. And so you're moving from a point of 0 up until where it stops. So x is 0 up until where it stops, where x is 6.9 meters. So this is 0 meters. And so we want to find out how much work is done. How much work do you do to stop the cow up until this point right here? Remember, in general, work is force times distance, but this is an assumption that it's a constant force. If you can recall, you can always visualize work in terms of graphs, so force and distance. If you have a random graph like that, then you want to compute the work done. It's pretty much the area under the graph. From your calculus, you can also do areas for shapes that are non-linear. Okay, and to do that, you're going to need an integral. So it's like you're going from 0 to 6.9. So there's an integral from 0 to 6.9. And that's a different way of computing your work. So your work is the integral that involves a variable force times the infinitesimal displacement from a position x naught up until a position which we're just going to call x final, for example. So we'll use the integral to solve for the work in this problem. Our initial point is 0 and our final point is 6.9. Those are our units of integration. And then we plug in the numbers. We have negative 20 in terms of newtons, and then plus 3n Newton per meter times the x, and all of that in terms of dx, because dx is the symbol for integration. So it's the infinitesimal point if you're thinking about areas under the graphs. When we do the integral of this, we end up getting negative 20x. Remember, there was a distribution of the negative, so this one is obviously going to be a minus. This is a minus. So this one right here is a minus. So minus 3x, you're doing the integral of that squared over 2. Remember, integral, if you have an x raised to n, if I'm doing an integral, I'm taking the exponent, you add 1, and then you add to the exponent. And that's what's happening here. Our exponent is 1, so 1 plus 1, and then you divide by another 1 plus 1. The limits of integration go from 0 to 6.9. So we can plug in these numbers. We get negative 20 times 6.9 minus 3 times 6.9 squared, all over 2. We don't need the second part of integration, because remember, if you plug in 0 to that and 0 to that, you're just going to get 0. So we only have one part of the integration. And if you plug in those numbers in your calculator, you're going to end up getting the work done being negative 209 joules. 200 negative 209 joules, and it's obviously negative because remember your force is in that direction, so it's negative, assuming this is the positive direction. So negative force produces negative energy. I hope you enjoyed the video. Feel free to share your questions and your comments, and looking forward to seeing you in the next video. Okay, thanks, bye.